Chapter 7 of Soil Science and Management. And today we're going to discuss soil, water, and the interactions therein. Um, these are the two most important things that we need to think about when we are looking into growing plants properly. And the soil is the structural component to those plants, but the water is what brings all the nutrients and maintains the plant's health. So as these two act together, there's many concepts that are there that are important for us to understand, and we really need to focus on those concepts and understand it. So this chapter today is going to be a fairly important chapter for the rest of the semester. Today we're going to be looking at the role of water in plant growth. We're going to define the forces that act on soil water. We're going to classify different types of soil water. We are going to discuss how water moves throughout the soil. We're going to explain how plant roots remove water from the soil, and we're going to describe how to measure soil water content. So starting with the most important concept, as I stated in the beginning of the lecture, plants require water, and it's just like a human being. If we don't have water, they don't have water, then they die. Plants are basically 50% to 90% water, and if they don't have that water, they start to look very wilty, and they will not be very turgid. They will lose their shape. They will droop down. They will curl their leaves. There's many different defense mechanisms that a plant has in the case of lack of water, and they're all very identifiable by looking at the plant and understanding that it could be dry. Water is used in a plant through the photosynthesis process. If we take water out of the equation, then we don't have photosynthesis and we don't have the food production that those plants are always accomplishing. Secondly, transpiration, when those plants are eating, we don't have that either. So if we don't have enough water, the plant can't consume the sugars that it's created, and it can't continue to grow and expand. It also affects nutrient availability because once the nutrients are within the plant, it needs to be uptaken through the osmosis process throughout the plant. We also have an issue with nutrient availability within the soil, because if the soil is too dry and there's not enough moisture to move the nutrients around, then we are unable to the plants are unable to access them. And then lastly, water is used by microbial growth, and as we learned in the last chapter, those mycorrhizae fungi are going to be affected, and they're not going to be able to grow and be healthy, and they will not be able to benefit the roots and do all of the things that they can do to help the plants. So some of the effects or causes of water stress are water shortages or droughts, and this can cause the plants wilting. When we have too much water, this actually will create an anaerobic condition because you will lose the oxygen within the water, and you can become other nutrients can become deficient because there is no ability for the plant to find the correct nutrients because it can't breathe. Many people don't understand that plants actually breathe as well, and these plants, when they're in standing water, are unable to complete many of their life tasks, because just like us, if we were underwater, we would be drowning. Well, a plant, if their roots are underwater continually, will be drowning as well. Some of the forces that act on water within the soil are gravity, and obviously gravity is going to be pulling that downward. Adhesion is being attached to other molecules, but this isn't so much like an adhesive where you have a sticky part, and then you have cohesion, capillary action, which is actually the water typically moving up instead of down. This is when the gravity is not as strong as the power is in the soil that is bringing that water to the surface. There is the soil water potential, the gravitational potential, and the osmotic potential. And so those three potentials are all things that have to do with the water moving side to side and up and down within the soil. And osmotic potential is the ability for the plant to uptake the water. We will learn that plants don't uptake water unless there is an osmosis reaction, and a plant must transpire to uptake water. There has to be an area for that water to enter into the plant in a pressure release, so as the tree transpires and expels water out through the stomates in the plant, in the leaves, then water is able to enter the roots. So it's a 1-to-1 ratio. So we have a couple different types of water. We have gravitational water, we have hygroscopic water, and available water. Okay, so these three, excuse me, different types of water are essential to understanding how water moves within the soil, because we can understand how the water will be moving throughout the soil. Gravitational water also can be called something known as saturation, and this is when you have filled all of the micro pore space, you filled all the macro pore space, you've filled it to excess, and it has additional pressure to be moved through the soil. And this gravitational water will be drawn downward through the soil, through the pores, through the channels, and out of the root zone. Once we have that water moved out of the root zone, we come to something called field capacity, and this is the ability for the soil or the root zone to hold the available water. These available waters are what the plant can access. So saturation is basically you've overwatered the soil and now certain amounts of that is draining away. Field capacity is kind of the Goldilocks syndrome of the soil. It's the just right. We have just the right amount of water so that the plants are happy. And then we have something called the permanent wilting point in soil water, and that is when we have such little amounts of water that the plant is not able to grow. So this permanent wilting point is basically equivalent to the death of the plant, because there just isn't any water for the plant to take up. Now, that's not saying that there isn't any water in the soil at all. What it's saying is the water in the soil is bound so tightly by the soil molecules, the plant is not strong enough to release the bonds of the water. This can be a problem because obviously if the plants are dead, then there's no point in managing them. So trying to avoid plants getting to the permanent wilting point or the soil getting to that point is important to understand, and that's going to come into how we irrigate, how we make sure we're managing all the different components of our soil to make sure we don't ever make it to that wilting point. So when we talk about water retention and movement, there's a couple of different things to understand. And when we look at water retention, every soil has a water holding capacity, and all of these soils vary in the amount of water it can hold. And this is based upon how much organic matter is in the soil, how much, what different particles are in the soil. So sand versus clay, what other nutrients may be in the soil that will hold on to water, how much micro and macro pore space, and then finally, how much compaction is within the soil. As we've discussed in the past, the more compact our soil becomes, the less water it's able to hold, because it just has little to no pore space to be held in. And then, as we talked about just a few minutes ago, water movement throughout the soil. There are a couple different ways water moves. We have the gravitational flow, and that's when we've, again, overfilled, oversaturated our soils, and we allow that water to flow downward. We have saturated flow. These are an unsaturated flow. These are just ways that water will move either down gradient, will move side to side. We discussed when in the particle type lecture, clay versus sand, and these saturated and unsaturated flows follow the sand, where you'll have straight down flow, whereas maybe in a clay soil you'll have more side to side flow. So these flows are dependent upon different types of soils and different types of soil particles within those soils. Okay, something we also need to discuss in the water movement for area is the wetting front, and this is the movement of the water through the soil. This can be important because sometimes we have issues if our soil hasn't been watered in quite a while, or we haven't had any moisture within that soil. The wetting front can actually move right past certain soils and not wet them. But this area is the water as it moves down the line and continues to wet the soils. So understanding that this is the front of water as it moves through the soil into a very dry soil. Then we have capillary rise, and this is when areas of higher potential are actually above areas of that are lower in elevation. So what I'm trying to say there is, after you have watered a soil, the water can flow down to a specific point and sit in a specific point for a while. And as the potential in the area above it becomes lower and lower and lower, the water will start to flow upwards because the potential becomes greater than the gravitational forces. So capillary action, as it's called, is actually the movement of a water molecule up through the soil. And actually this capillary action can bring the water right to the surface of the soil and can allow that water to then be on the surface of the soil and potentially evaporate. And so the last one, soil horizons, and this can be affected because if we have different soil materials within those different horizons, it could affect the flow through the soil. And this is going to go back to maybe a concept we talked about earlier, was the hard pans. Those soils can be in different horizons, and they can create different movement issues for the water once it's in the soil. Okay, so when we're talking about measuring soil water, we're looking at the preferential flow, and one of them, this preferential flow is something that I've talked about before, and this is when a water molecule would like to follow the path of least resistance, and this can basically be seen by water as it flows downhill. It's very hard to push water uphill and almost impossible. The water is going to find the area in which it can flow downward the fastest using gravity and other forces. And these preferential flows will find those channels or burrow holes or other big macro pores to allow the water to flow through. When roots are gathering water, it also is affected by that soil water potential, and we talked about capillary action, and that capillary action is very similar to soil water potential in the fact that it has to do with high and low potential. When to think about this, if you were to think about a sponge, and if you were to think about a very wet, full of water sponge, and you were to place that in a bucket of water, it would not attract much more water. It would just sit there with the amount of water it had when you put it in the bucket. But if we were to take the same style sponge as it was very, very dry and you were to place it in the bucket, it would absorb a lot of that water. And that is because the soil potential in that dry sponge is much lower than the potential of the water, and then thus allowing the water to infiltrate and flow into the sponge. This is the very same thing that is happening in a root, and the plant is removing water at the top of its structure through the leaves, and it's then allowing those roots to absorb water and flow those waters through the tissues within the trees or plants and allow them to be used throughout the plants. So coming back to measuring of the soil water, we have gravimetric measurements, and these are going to be based on weight and volume, and this is going to go back into your particle densities and your bulk density, and we can start to understand how much water we are able to hold within a certain soil. And we also have some materials that can be used. So the potentiometer is basically like an artificial root and will be put into the ground and will simulate the osmotic action of the root trying to suck up the water, and can determine if it is being resisted based upon forces that the soil is putting on the water. And then lastly, you have the resistant block, and that is going to be a block that measures soil moisture by placing it in the soil moisture. Also, something not discussed here is we have soil moisture meters, and these are used by irrigation systems to understand water in the soil, and that is done by electrical current. And if the electrical current can be flowed through the soil, then that means there's a lot of enough water in there, and it's not an issue. If the electrical current does not pass through the electrodes, then there is not enough water within the soil. So where does water go? Water eventually will like to make it to a water table or to a hard surface underneath the ground once it's in the soil. There are other things that can cause that to not happen. We have the capillary action, we have plant uptake, we have evaporation. We also can have ponding that can occur due to a soil's lack of ability to accept the water. And then we also have physics of where water will grow. And this is going all the way back to the beginning of the lecture, when water will want to go through the easiest way possible, and it's going to flow through these bigger channels, bigger pore spaces, and then will flow through the smaller pore spaces once all the bigger ones are being utilized. So in summary, we talked about soil water potential. We talked about the types of soil water. We talked about how water moves and penetrates into the soil. We talked about different soil types and how those can be affected by water movement. And we talked about water absorption. Something I would really like you to focus on through this lecture is the three types of water: the saturation, the field capacity, and the permanent wilting point. Understanding how those three water potentials act upon a plant. So understanding those three is going to be important for testing and essays. Thank you so much. I hope you enjoyed the lecture, and I will see you next time.